Alright, so let's review over what to expect on this final. So the review goes through all the concepts that you should be looking over and practicing in order to prepare yourself for the final exam. So it goes back through all the material that we've covered throughout the year. First semester was basically an introduction to the language that physicists use to study motion, and beginning to look at developing Newton's laws to understand why objects move the way they do. So under kinematics, we learned all of the equations that we would use to describe objects moving with constant velocity and constant acceleration. So the first point here to review are the equations and the kinematic curves. Motion maps, how do you show constant speed, changing speed, positive direction, negative direction. So let's take a look at that first. So for constant velocity, we can describe graphically an object moving in one dimension with constant velocity with lines that have slopes. So I can put an object that starts here and slopes up. What that tells me is that the object has some initial position x0. So where that is located, if you have a number line, this is the negative direction, this is the positive direction, this is the x-axis. This object is located at some position to the right. So at time equal to 0, that's where the object is. Now, the slope tells us the velocity. And because it's a line, that means there's only one velocity to worry about. And so on our motion map here, what we could use is an arrow that is pointing to the right. And after a certain period of time, the object is at a new position. So this position here is marked at this location, which could be found, extend that axis to this location right here. But since the velocity is still the same, then the length of our arrow here will be identical. So this arrow and this arrow are the same. On a velocity time graph, all objects moving with constant velocity appear on velocity time graphs as horizontal lines, which are representing the value of the slope of our position time graphs over time. So the fact that this value is a constant value, could be any positive number, +2, +3, would all count as valid representations of that slope. Well, any positive value would be above the t, so that's your initial velocity, but then it doesn't change, so that would be a horizontal line that continues on. So this represents the non-changing velocity that that object has. The last curve is acceleration versus time, and that will be the value 0, because by definition acceleration is a description of the rate of change of velocity over time. If we're dealing with constant velocity, then that means that the velocity isn't changing. So the acceleration must be 0. If we look at an object that starts here and goes down this way, that's an object that is starting at a position that is further to the right, like so, and has a velocity that is negative, because the slope is negative, so it's moving to the left. And so it's making its way towards the origin. At this time, somewhere around here, if you project that further, so some time in the future, it will actually arrive at the origin if the motion were to continue. Now this velocity is constant and negative, so that would be a line that belongs beneath the t-axis. But the acceleration is still 0. Now let's talk about real quick the equation for a line like this one is x equals the velocity times time plus x initial. I can move x initial to this side, which is the same thing as saying delta x, and that must equal v times t. So displacement equals velocity times time. That's the whatever variables you call them. I can call them any letters that I want. So it's not to confuse that if we're talking about up and down motion, that might be positive, because we're talking maybe about an elevator going upward. We would just swap out this x for a y, but it doesn't change the fact that this whole quantity is the displacement just in a particular direction. So we can always change the letters around, but the concept is that displacement equals velocity times time. Now for constant acceleration, it gets a little bit more complicated, and that is because we're working with objects whose velocity do change over time. So this is position time graph, velocity time graph, acceleration time graph. So first of all, since the acceleration is non-zero if we're dealing with constant acceleration, so on an acceleration time graph, all the accelerations are horizontal lines. You could have a positive acceleration, for instance, that doesn't change. That would mean that the acceleration is constant. That means going backwards this way, that the velocity time graph will have a positive slope. So it could be a line that looks like this, it could be a line that looks like that, it could be a line that looks like that. All three of those velocity time graphs go with the same acceleration time graph. They all describe an acceleration that is positive and constant, but each one of these means something different. This line here starts with a negative velocity. That means that our object is moving to the left, and it's fast because it's far away from zero. So this arrow is bigger now than it will be later because this line is heading towards zero, so that means these arrows are getting smaller. When it hits zero, it comes to a stop, and now the velocity is entering into the positive section, and so that means that the velocity is now going to start picking up, but in the opposite direction. So the positive acceleration first caused our object with this initial negative velocity to decrease its velocity over time, and then when the velocity hits zero, the same positive acceleration causes the object to speed up in a positive direction. Using the money analogy, if you have the velocity could represent money and the acceleration represents the rate at which you earn or lose money. So if you have a positive rate, then that means you're gaining money over time. So the way you would explain it this way is that you start out with no money, even less than that, you're in debt. And by increasing the amount of money you have over time, that takes you out of debt until you reach the point where you have no money, left over, nothing saved, but you don't owe anybody else any money, so you're debt free. Now all the money that you earn is money that you can keep and store. So this graph here represents us starting with no velocity and immediately increasing from rest. So that would just be sort of this top row of arrows. And this one, we're starting with a speed. So basically from here on out would be how you would represent the top line. But all of these situations are related to the same positive acceleration. So now, what do these graphs translate to on the position time graph? Well, the additional piece of information, notice I didn't put the axis here. Usually we'll put our x-axis or our y-axis. I didn't put that here because starting out with this information, we first of all didn't know what the starting speed was. We just made up 3 different numbers, 3 different places to start them at the graph, but we weren't told how fast the object was moving. But the other thing you don't know is where the object is. So I don't know if the origin is over here or if it's in the middle. So I don't know where to start this graph. So without being told, you can make a guess. Now, this one, we're moving in a negative direction first, so I might want to place this up here. And we're starting off fast and negative, so the tangent line should be steep but pointing downward. And over time, the slope is getting less and less until we reach this point where the slope is horizontal, and then the slope is increasing but positive. So this is a parabola that looks like that. If we were trying to draw this position time graph, then it's basically the graph that occurs from the right side of that dashed line. And if we wanted to draw the position time graph for this line, it would be really like starting whatever is to the right of this dashed line. Because why that would make sense here is that this is already starting with a slope, just like this is already starting with a velocity because it has a value, and then the velocity is increasing, so it's just going to continue to curve upward. Right? So that's the essentials of how you think through the kinematic curves. So let's take a look at the next topic, which is known unknown strategies. So I gave you the equation that represents constant velocity. The equations that represent constant acceleration, there are many because you have 5 kinematic variables: displacement, time, v initial, v final, and acceleration. So the equations are the definition of acceleration, which is a equals change in velocity over time, which is the same thing as saying v final minus v initial over time, or can also be rewritten, solved for v. All of these represent the same thing, but this has no delta x in it. Another equation would be delta x equals 1/2 acceleration times time squared plus v initial times t. This has no v final in it. So if you remember where we derived this equation from, it's a velocity time graph where we started out with some initial velocity VO. Delta x on a velocity time graph represents the area. So to find the area of this, you need to do VO times T, and then the triangle is 1/2 of this is some velocity up here. This would be delta v times t. But the definition of acceleration is delta v equals a times t. So the total area equals this 1/2 delta v times t plus VO times t. But I can substitute in for delta v a times t, and you get 1/2 at times t plus VO times t. So that equals, if you combine the t's, 1/2 times a times t squared plus VOT. That's where that equation comes from. The other equation was delta x equals v final times t minus 1/2 at squared. And this one has no v initial. So that's saying that we don't know what this value is. So what you do is you find you do know what this velocity is. This is our v final. You find the area of the full rectangle, which is what vf times t is, and then you subtract the area of a triangle that has the same dimensions, because this is just a rectangle that you cut in half, so this triangle has the same area as that triangle. So the area of this triangle up here is still 1/2 at squared, but you're going to subtract this area from the full rectangle, and you're left with the same area underneath, which is still this delta x and this delta x are the same thing. It's just, do you know v final or do you know v initial? That's the difference. And then the last one, combining these equations, is the equation where you don't have time. And so you get v final squared equals v initial squared plus 2 times acceleration times displacement. And so that's with no time. There is another equation, but we rarely have used it this year. It's one that doesn't have acceleration in it. So it comes from the fact that this is the constant velocity formula. Displacement over time equals velocity. But when you have an acceleration, then that velocity is really the average. And if you want to compare that with the initial and final velocity, then you can set delta x over t equal to v initial plus v final, and then divide by 2, because we're taking an average. So you're taking these two velocities and dividing it by 2. This only works because we're dealing with constant acceleration. So these two velocities have equal weight in the average. So I can just add these two values and divide by 2, and I get the average velocity. So that's a way to bypass using acceleration only for constant acceleration objects. So this one has no acceleration in it. So those are the big 5. So the way we problem solve with those is doing a known unknown. And remember, you always need 3 knowns to solve for one unknown. And there's always one unused variable. And that's the one that's not in an equation that we had written up above. Alright. So now let's look at the next concept on this list, which is free fall. Objects falling under only the influence of gravity. All objects on Earth fall with a constant downward acceleration of 10 meters per second squared. It's nearly because it's actually negative 9.8. We round it up to 10, which is acceptable for the use on the exam. All objects having that acceleration change their velocity at a rate of 10 meters per second per second. So if you were to look at their speedometer as they fall, every second that goes by, the speedometer needle will increase an additional 10 meters per second every second. Because it's accelerating, every second that goes by, it's able to cover more and more distance. So the distance it covers in the first second is less than the distance that it'll cover in the next second. And as each second goes by, it's able to cover more and more distance. But the acceleration is not dependent on the mass if it's only due to gravity. So this is an important concept that will come up on the exam many times. You have two objects that fall from the same height and hit the ground below. They will hit the ground at the same time because if they're only acted on by a force of gravity, this FG looks like that. This FG looks like that. So gravity being the force between the object and the Earth, this object is being pulled harder than this object. Well, we can use Newton's second law, F1 equals ma. So the acceleration would be the unbalanced force divided by the mass. So the unbalanced force in both cases is Fg, which is mg in the negative direction, divided by the mass. So it's true that the force of gravity on this bigger object is larger than this one, so it's being pulled harder, but that same force has to pull, this greater force has to pull more mass. This weaker force pulls less mass. So you would think less force means less motion, more force means more motion. But more force here has trouble moving this object because it's bigger. This less force has an easier time moving this object because it's smaller. But the way gravity works is that because gravity is proportional to the mass, it allows for these two objects to fall with the same rate. So these two masses in the equations cancel, and so no matter what mass I have plugged in, I would get negative g, which is negative 10 meters per second squared. So by finding gravity, I do, for this object, let's say it's 5 kilograms, it would be 5 times 10 newtons per kilogram. So you get 50 newtons up here, but I'm going to divide by 5 kilograms and get 10 meters, negative 10 meters per second. If I do that with a bigger mass, if this is 10 kilograms, I do 10 times 10, that's 100, but then I divide by 10 and I get back 10. So again, the masses always cancel out. So despite their mass, two objects starting from the same height take the same amount of time to fall, they hit the ground at the same time, they pick up the same amount of speed. This is all with the presumption that our Freebody diagram is just an object with gravity acting on it. If there are any additional forces in that diagram, then what I've just said is not true. They would fall at different rates, they would take different amount of time to hit the ground, they would hit the ground with different speeds. So this is the statement that they hit the ground at the same time if they're dropped from the same height because they're accelerating at the same rate. That is all assumed based on this Freebody diagram right here. All right. Now, also in free fall, in your review, it says that as a ball is thrown up, a force is applied on the ball, causing it to accelerate upwards. But the applied force disappears the moment the ball leaves the thrower. So an object that is thrown up in the air As long as it's in your hand, you're guiding it. And so you're able to make the ball go as fast as you want it to. You can make it go in whatever direction you want it to, because you're in contact with the ball being thrown. But once it leaves your hand, you have no other influence on it. There are no other mysterious forces acting on it. If we ignore air resistance, then we're back to this free body diagram. So the ball being thrown straight up in the air will lose its y velocity, come to a stop, dead stop at the top, still with a negative 10 meter per second squared acceleration downward. So without that acceleration, that ball that had gotten to some maximum height would just stay there, just stay floating. But it's immediately pulled back down at the same rate that it was slowing down on its way up. So that's one-dimensional motion. If there's no horizontal motion at all, there's no motion to the right or to the left, it's all vertical. You throw a ball up, it slows down, it reaches zero. The vertical velocity, which is all the velocity that it has, equals zero. And then it comes to a stop, accelerates back down. All the while the acceleration is negative 9.8. Okay. So let's look next at the dynamics section. Alright, so here these are statements of Newton's three laws. The first law, which we call the law of inertia, says that objects at rest stay at rest, objects in motion stay in constant velocity types of motion, unless there is an unbalanced force, outside forces acting on it. So I have that stated in part A as if fun equals zero, which it's hard to get away from forces when you're in the presence of the Earth with gravity pulling you down, but you can experience, at least theoretically, no force in deep space. But here on Earth, where we're dealing with forces all the time, we can still get this situation where objects stay at rest or objects stay in motion as long as the forces that are acting on it are balanced. So if fun equals zero, then acceleration must equal zero. So acceleration equal to zero just means that the velocity cannot change. So if you initially started with no velocity, then you remain with no velocity. If you initially started with positive velocity, you stay with positive velocity. If you initially started with negative velocity, then you stay with negative velocity. You keep the same speed moving in that particular direction. The second law is fun equals ma, that forces cause acceleration. Forces are responsible for changes in motion, but a force causes a certain acceleration depending on the mass of the object. The more inertia an object has, the more mass that it has, the harder it is to accelerate. So it requires more force to cause a big object to accelerate than it does a small object. Mass is always in our class measured in kilograms, and it describes the amount of matter in the object, which is another way for us to quantify the property that objects have that we call inertia, which is a body's resistance to changes in motion. So if you think about the UCM lab with the stopper spinning on the string, and you get the question that, right, what happens when the string breaks? It flies off in a path that's tangent to the circle, and that's because when the string breaks, there's no more forces acting on it. So this is the path that the stopper was following, and it had a velocity in this direction at that moment. So if the string was cut, then this is the path that the stopper would follow, and that's because there is no more. When the string was still attached, there was a force pulling the stopper towards the center. That's our force of tension, which in this case is centripetal force for the system. But once that force is gone, then we're left with moving off in this straight line path. Other examples which come up on the next page where this can be applied is the fact with like a hockey puck traveling along ice, which again, if you assume is frictionless, then there's no horizontal forces. There's gravity and the normal on a hockey puck, but they cancel each other out also, so we don't have to worry about that. We could also think about a rocket in space traveling away from any planet, away from any gravity. And so we take that case where we have a rocket that has the ability to fire thrusters on all sides, is initially moving in this direction with constant speed. Alright, so had already fired the rockets on the thruster on the left, so it was propelling it to the right, but now those rockets are off, and so now it's just drifting with constant speed over to the right. There are no forces, and so there's no acceleration. But the object doesn't need a force to stay in motion. But now we're going to change the path of this rocket. So what we're going to do is we're going to allow the rocket to fire the thrusters this way. What that's going to do is going to provide a force that is, let me put that here, that's upward. But now at the same time, so that force is upward, that is going to cause the a velocity, so that force will cause an acceleration, which will cause a change in velocity for the rocket just in that direction. So that means that while the object is still moving to the right, the object is now going to gain motion upward. But let's just take for an example that these rocket boosters are turned on and off really quickly. So it's just a switch on, off. When you turn the boosters on, that's when, for the duration that they're on for, however short, that produces a force. Fun equals ma, so that force will produce an acceleration, and that acceleration over time will cause there to be a change in the velocity in that direction. So there'll be, let's say now that this red arrow represents the velocity in that direction that it picked up. So I'll call that Vy. But if at the same time this object was already traveling to the right, we'll call that Vx. And so now immediately after it's gained this Vy, we shut the thrusters off. With no additional forces, then whatever motion the object has now, it will stay with that motion. Objects in motion will stay in motion. But what is the motion now? The motion is a combination of the two motions that the rocket has now. It's still moving to the right unaffected by the thrusters, but it's also now moving upward with a new velocity. So the combination we put together using Pythag, and it gives us this resultant. So that's the new speed of the rocket. It should be bigger than either Vx or Vy. So I'll call this V with these bars around it. That's the square root of Vx squared plus Vy squared. So V is going to be greater than Vx and Vy, both, but will be less than the arithmetic sum, Vx plus Vy. This is, so as not to get you guys confused, this was and, not plus. So meaning that it's greater than Vx, it's also greater than Vy, but it's less than the value you would get by doing Vx plus Vy. So if you need a numerical example, let's take the case that we have a 3, 4, 5 triangle. This is 3, this is 4, so this must be 5. 5 is greater than either 3 or 4, so it's greater than 3 and 4, but it's less than 3 plus 4, which is 7. Right? Because the 5 came from Pythag. Right? So that's the way the vectors work. So we know that if the object was moving at 3 meters per second to the right and now gained a 4 meters per second speed upward, that its new speed is now 5 meters per second, and that motion remains constant throughout the remaining part of the motion. Okay, so remember, this is the case where we switch the boosters on and off. Right? So it gives some velocity upward in this direction, and so now it doesn't continue to accelerate upward. So it gained a little bit of velocity in a very short period of time, and now we combine these two velocities together to show what the resultant will be. So an observer looking at this spaceship from the outside will see the spaceship drift off in this direction with constant velocity. All right. Now, if the boosters were to continue to fire, then this arrow will be like what gravity would do, because if the boosters provide a constant force and you have a constant acceleration, and the rocket will continue to move in upward with an accelerated rate, so this arrow will keep getting bigger, and you would anticipate that maintaining the same velocity to the right, that the new path that the rocket will follow will be a curve. So the rocket will drift off in this direction here and continue to speed up. So the rocket will always continue to move to the right if this is 3 meters per second, but this will grow from 0, 1, 2, 3, 4, 5, and keep speeding up that way. So the speed will increase from 3 to whatever value it goes up to, depending on how long it spends accelerating. Okay, so that is a good example to think about. Let's go back to under unbalanced forces. We have some definitions you should know. Again, mass is in kilograms. Inertia is how much matter is in an object. Weight is the force of gravity acting on a mass. And so we're here on Earth, the gravitational field strength, little g, equals about 10 newtons per kilogram. That means that gravity around the Earth pulls things in. Depending on your mass, the force will be equal to 10 newtons per kilogram of mass. So you put a kilogram right here, and there is a force on that kilogram of mass of 10 newtons. If you put 2 kilograms in here, then there's a force of 20 newtons that is ready to act on that object. So again, this is the field strength, 10 newtons per kilogram of mass that you have. So if you want to find Fg, that's just mg. So you take the mass, which is, something, this particle here will have a mass of 2 kilograms, whether it's near the Earth, far away from the Earth, near the Sun, on another planet, in another galaxy. It'll have that 2 kilograms of mass, which describes the amount of matter it's made of. But the weight, how heavy you are, depends on how much gravity pulls you. And that depends on the field strength, which around the Earth is about 10. Around the moon, near the surface of the moon, it's about 1.6 newtons per kilogram. But the apparent weight, how heavy you feel, is the normal force. So gravity wants to accelerate us. If we accelerate at 9.8 meters per second squared, we would feel like we were in free fall. But we're not, because the floor is pushing back on us. So we're feeling the resistance to what gravity would otherwise make us do, pulling us downward. So we feel whatever the normal force is. That is different than how much you weigh in certain circumstances. In everyday circumstances where you're in your house, you're sitting down on your couch, you're walking around on flat surfaces, Fg and Fn are balanced, so you feel your whole weight. But you can set up situations where you feel either lighter or heavier. So let's take a look at just a couple examples of that. So one case would be being in an elevator. So if you're a person inside an elevator, the elevator is moving upward. There are always two forces acting on you, the person. You have Fg, which is how heavy you actually weigh. And then you have the normal force, which is how heavy you feel. And if the elevator is moving with constant velocity, then you feel your weight. But now let's take the case where the elevator is now accelerating upward. Well, fun equals ma. If the acceleration is positive, because this is the positive direction, then fun has to be positive. So that means I need a net force that is upward to produce the acceleration. So it wasn't enough to have a normal force that is the same size as Fg, because canceling Fg out means that there's no force left over to accelerate you in the inside the elevator. So Fn has to be so if you have your mass and you know what the acceleration of the elevator is, that determines the amount of force that's needed to accelerate you. Fn has to be that much more than Fg. And you can always get to that result by saying that the normal force minus Fg has to give us our unbalanced force, because the difference between the two gives us what's left over, which is the unbalanced force. And to find Fn, you add Fg to both sides, so you get Fun plus Fg. So like we said, we add whatever the requirement is for the amount of force to cause this acceleration. We add that to your weight. So because this is going to be, because we've added on this number, it's going to be a bigger value than Fg. And so since Fn will be greater than Fg, you feel heavier. If we were descending with a constant acceleration, then so we were picking up speed as we were going down, then you need a net force that's downward. So this would be negative, and this would be negative. So even if you left this the same, since Fun will have to be negative, this you'll be subtracting Fun from Fg, and so Fn will be less than Fg, and in those cases you feel lighter. Now, if here we're dealing with one-dimensional motion. So if you knew the acceleration, for instance, was 3 meters per second squared, and you wanted to know how fast the elevator would be moving after 3 seconds, given that you have the acceleration, the time, and v initial is 0. If you're starting at the ground floor, for instance, then we would use the equation that doesn't have delta y in it. So that would be v final equals at plus v initial. And so 3 times 3 is 9, plus 0 is just 9 meters per second. So that's how fast you'll go. Now, you can get the same sort of changes in how you feel you weigh by moving around in circles at constant speed. So those are the cases where you're moving over a hill or through a valley or through a little loop-de-loop there. And actually, I'll move this over here. So if you're going over a hill and you're at the top of the path, you have gravity and the normal force. But if you imagine the circle that this makes, the center of the circle is beneath you. So it's a requirement to be in a circular motion to have a centripetal force or a center-seeking force. Your velocity is tangential. Your acceleration is centripetal. And so you need a net force that's acting towards the center. Notice here again that acceleration and velocity for circles are perpendicular. Acceleration and force are both centripetal. Force and velocity are perpendicular. Centripetal force and velocity are both perpendicular. So the way we come up with our centripetal force for these situations is you do the big force minus the small force. So the one that's pointing towards the center minus the one that's pointing away from the center. So if you knew how heavy you felt half your weight, for instance, then Fn is going to be half the size of Fg. So if Fg was 100 newtons, if you felt half your weight, then your weight is still 100 newtons, but Fn would be 50 newtons. You would do 100 minus 50 and get 50, and that's your centripetal force. Now, if you wanted to find out how fast you'd have to go around this circle, or in this case over this hill, in order for you to feel half your weight, you have to use the equation for circular motion. Now, you might have it on your index card as AC equals v squared over r. So we can rewrite that as v squared equals AC times r. So finding the centripetal force, that gives you fun for circles. Then you can use fun equals ma, given that you have the mass, you can figure out the acceleration. And having the acceleration, you can find the speed, but I'd have to give you an additional piece of information, which would be to know what this radius is. Once I give you r, then you can work out what v is. Now for the going through the valley here, it's a different situation. Down here, because the center of the circle is above you, you need a bigger force towards the center, which is up this time. So whatever Fn is, it's going to be larger than whatever Fg is. Now if this is the same person, then the Fg here is going to be equal to the Fg here. But now when I write Fc, I'm going to be going the other way. I'm going to be saying Fn minus Fg. Fn is towards the center this time. Fg is away from the center. So you'll feel heavier going through this valley. You'll feel lighter going over the hill. Now in the loop-de-loop, when you are upside down, the center is beneath you. You've already got gravity acting on you. Now, depending on how fast you go through that loop-de-loop, it may require that you have more force, because we can combine this with fun equals ma. Put an m here, put an m there, and this is Fc, because fun equals ma, which is mv squared over r. So if you go faster through this loop, that requires more force. Well, gravity's all you have, so you would need more force to push you down through the loop. The additional force that could push you down if you go through the loop fast enough is a force from the seat, because you're upside down, so there's an additional force from the seat, Fn, because this is the seat, and so you'd be upside down, and so the seat is pushing you this way. So when I write Fc for this situation, Fc equals Fg plus Fn, because they're both pointing towards the center. So they add together. When they're pointing in opposite directions, they subtract, and I always go with the bigger one to ensure that I get a positive number when I do the math. But when they're both pointing in the same direction, you add them together. Alright. The other concept on the first page that's also important is action equals minus reaction. So that's Newton's third law. That comes from the definition of force, that through every interaction, two forces are always created. The first force is the force of gravity. And so if you take a situation where you have a table, and we'll place an object on the table, there's gravity acting on this object, and it doesn't move, so there must be a normal force acting on the table also, on the box. So these forces remain balanced, but each one of these forces gives us its own pair force. So a lot of people had made the mistake that these two forces are what we're talking about here, because they are in fact in this situation equal and opposite to each other, but that's not what Newton's trying to describe here. This is gravity is the in this case F on box by Earth, and what he says is there is another force that's not on this Freebody diagram, that is a force that the Earth is feeling from the box. So the Earth is down here, and the Earth is feeling a pull upward, and that's equal and opposite of that force. So that's our Fg universal equation. So force of gravity is universal between any objects that have mass, whether it's the Earth and a person, or two people that are sitting close to each other, two people that are far away. Any two objects that have mass, you can calculate the force between them. But gravity really makes a mark when the masses are big. So that's why the Earth's gravity is so much more important to talk about, because the Earth is so massive. But otherwise, there are these forces everywhere, but most of them are too small for us to feel or to affect anything. But it exists. So the Earth is being Now this force that the box is pulling up the Earth by is big enough to be felt. So, you know, that same force pulling on the book, if that table wasn't there, would cause that book to accelerate at 9.8 meters per second squared. But the same force pulling the Earth up is insignificant because of the fact the Earth has so much mass, and that goes back to F equals ma. The forces are the same, but because the masses are different, their accelerations will be different. The box with the smaller mass will have the higher acceleration. The Earth with the bigger mass has the smaller acceleration. So the Earth barely is affected, and the box could be accelerated at a high rate, given that these were the only two forces that existed. But there's this normal force as well. So that's the force on the box by the table. But Newton says that there is another force, that is the table pushing back on, or the box pushing on the table. Now you might have mistaken that to be gravity. Gravity looks like it's a force that's pushing into the table, but that force is describing a pull from the Earth, not a push from the table or from the box. So these normal forces, so there's a normal force here that the table is feeling from the box, and that's a completely different force that's not on this diagram, and that these two guys are the same. These two guys are linked. And so that has more to do with the fact that you know, everything is made of these negative charges, and if you have the same charges, they repel each other. So these normal forces are really due to electrical forces between two surfaces, whether they be our hand and a wall, or this box and the table. But you know, we can't put our hand through the wall because of the repelling forces that the atoms in our hand exert on the atoms of whatever we're pushing. But the closer, those electrical forces behave very similarly to gravity, in that the electrical forces are dependent on the distance in the same way, the inverse square law. So the closer I bring my hand to a wall, the more force the electrons push against each other with. And so our bodies are have evolved to sense the changes in those electrical forces. So when we get really close to pushing a wall, you know, we push harder, we feel that we're pushing harder because the electrons exert forces on each other that are larger. And so our bodies, through our nervous system, can sense the changes in those electrical forces. So it's not because we're actually in contact with the wall. If we're trying to touch the wall, there's always this space in between, because if the atoms in your hand combine with the atoms in a wall, then you become part of the wall. So that doesn't happen. And from a quantum mechanical standpoint, it's hard to even describe electrons as being these like the little particles that I drew up on here. So it becomes very abstract to start thinking about them coming together and making them into new atoms and things like that. So the forces are strong enough that it's very hard for us to try to push our atoms and mix them up with the atoms in any other surface. So we never actually really touch anything but we call them the normal force when it appears to us that they're in contact with a surface. But just, realize that that is, again, because of electrical forces. So going back now to this point, during any collision, when two objects collide, no matter what their motions are, those internal forces, these action-reaction pairs, are always equal and opposite to each other. So you've had the question before about the fly on the windshield. The fly hits the windshield hits the fly. Those two forces are always identical. It doesn't matter if the fly ran into the windshield while the car was at rest, or they were moving in the same direction but the car was moving faster than the fly, or they were moving towards each other and had a head-on collision. It wouldn't make a difference. The forces that they exert on each other, whether they're bigger or smaller depending on their motion, will be equal and opposite. So the fly exerts the same force on the windshield as the windshield exerts on the fly. The results of that particular collision can be thought of using Fun equals Ma. So with the car having such a huge mass, it experiences a small acceleration to give us the same force that a tiny fly would experience in that same collision, which means that the acceleration must then be large on the fly. And that's what ultimately gets the fly, is the change in motion. The fact that the fly is forced to come to a quick stop is a direct result of the fact that for that mass, that force can do a lot of damage. But that same force on a big mass doesn't really affect the motion of that object anymore. So anytime two objects collide, the damage comes from a combination of the forces that are acting together and the fact that those forces cause these decelerations when those bodies want to keep moving. So objects in motion want to stay in motion, so when you see a head-on collision, the whole front end is completely smashed in. That's because if a car was moving forward and then all of a sudden hits an immovable object, the front is forced to stop as soon as it hits this, let's say it hits a wall. It's forced to stop immediately, or within a very short period of time, fractions of a second. But the back end of the car keeps trying to move with the same speed that it had. Well, that pushes the car into the wall even more, and so that's where you get the the damage done on the front end of this car. Okay. So let's try to move on a little bit here. So what we're going to go to the next page. Alright, so we talked about the rockets. Again, the ice puck would be the same situation. I could present questions to you in either one of those contexts, and it allows you to think about ignore air resistance or any frictional force. So as long as you understand that there's unbalanced forces lead to acceleration, balanced forces lead to constant velocity. That's important. Elevators and boxes. Imagine forces are applied to such objects like elevators or boxes. How can you determine the type of motion they have using forces? So an example of that is you're moving a box across the floor, you're pushing it, some force, and it's moving with constant velocity. What does that tell you? It immediately tells you that there has to be an opposing force that is equal in strength to the force that you're applying. Why? because the forces have to be balanced in order to create constant velocity. Now you look at your system and you say, then you can ask as an afterthought, what is that force that's acting against my motion? Well, the only things that the box is in contact with are you, but you're providing the force that's forward. The Earth, which is underneath, and that's pulling it down with gravity, and you have the surface pushing it up with the normal force. And so I haven't drawn those here, but those two forces cancel each other out, up and down, so there's also constant velocity upward. But how do I know friction? This force is here. Well, friction is the obvious culprit here, because out of the different objects that the box is interacting with, you can only push in the direction that you're pushing. Earth can only pull downward towards the center of the Earth, but the surface can resist motion horizontally, which is our frictional force, and vertically, which is our normal force. So again, if you know what the motion is, you know that the forces have to either be balanced if it's constant velocity, or unbalanced if it's constant acceleration. Review all your forces and know the difference between static and kinetic friction. Okay, so what's the difference? So you might recall a graph of some of friction and some applied force. So if we start at rest, V initial equals 0, then if I apply a force and get no motion, then that means that there must be a force that is equal in strength to the force that I applied. Right? So because it didn't budge, so there must be just as much friction pushing against me as I'm pushing against the object. So I push a little bit harder. So friction pushes back with more force if, again, that the force that I apply here is not enough to get the object moving. So this trend continues until finally you apply a little bit more force, and that force is able to get the thing going. So the object now starts to move, and you realize that once you get the object into motion, it's easier for it to slide across the surface. We had talked about that one theory is the fact that most surfaces, even though they appear smooth, are at a microscopic level are pocketed with these little crevices. And so same goes with an object that you have on top. And if two objects are sitting on top of one another, these little pockets sort of interlink. But if you get the thing to start to move, then instead of settling into these grooves, they just sort of slide over top. So it gets a little bit easier for many different types of surfaces and substances to keep an object moving over top of it once it's already in motion. And so what you find is after you reach this peak and you get it to move, that the amount of friction that you get pushing back is less. So it drops, and then no matter how much more force I apply, you always get the same amount of friction out of it. So what this defines here is the difference between static friction, and that's the friction where the object was at rest, and kinetic friction. The definition, or the equation that describes friction, is mu times the normal force. These are the two things that affect friction. Mu describes the type of surfaces, so these are all experimentally determined values that help us to rate different types of surfaces. Fn is the amount of force that the surface pushes back on an object. So the closer these two surfaces are together, the harder they push back, the more friction you would expect to see. Mu, one factor of mu could be related to the types of, whether the surface is smooth or not. It may help to determine whether there are more of these grooves or, larger grooves at a microscopic level. But, for our purposes, there are numbers that can be experimentally determined. But obviously, this friction here, static friction, can range from anything from 0 all the way up to this maximum value. So this value of friction here is called FFS max, and that's equal to mu, which is the mu value that produces this large force here. So I'm going to call this mu s times the normal force, because the normal force might not change. So how is it that the friction can go from being so large to dropping to this value? That's because the mu value changes. For FFS in general, like we said, it ranges from 0 to whatever that FFX max is. So it could be any value that is less than or equal to mu SFN. And then kinetic friction equals mu K Fn. But in general, I've never used the K, because if I want to distinguish between kinetic and static, I use the S notation to make sure you recognize that we're talking about static friction. And if we're talking about kinetic, I'll just say FF without the K for kinetic. All right, know how to draw the different types of free body diagrams, how to quantify them, when to tilt them, review your trig, vector components, ramp angles. So if I ask you to come up with a free body diagram for this block, it's got a mass m, this angle here is theta, then this is the situation where you would tilt the axis. This is the x-axis, and then you tilt the y-axis to be perpendicular to x. The mass gets shrunk to a dot, place at the center. You have gravity acting on it. The angle at the base of the ramp is this angle right here. Alright, that's again because if this is like our y-axis, and this is like our FG direction, and you can see that if this represents our x-axis, this angle here has to be 90 degrees between our ramp and this perpendicular. This angle here and this angle here, let me put it in red, have to add up to be 90 degrees, but so does this red angle and this orange angle. So this orange angle here must be theta. And so this is the y, this is the y, this is FG, this is FG, so that angle must be theta. In addition to gravity, we've got this normal force acting up that way, and if it was frictionless, then we're done. And what this box would be doing is, if it's at rest, would immediately start to move down the hill. So how would you determine the acceleration? Well, you have to break up your force into components. One that is acting opposite to Fn, and one that is acting perpendicular to Fn or along the ramp. So this is Fgy, that balances with Fn, and then this Fgx is the component that's left that is in the direction of the ramp that causes the box to slide. So fun in the x direction is Fgx. Now, to use your trig, this is the opposite side of the triangle with respect to that angle. So it's the hypotenuse, which is Fg, times the sine of the angle, which can also be written as mg times the sine of that angle. Fgy is the adjacent, so that's Fg cosine of the angle. So that's what Fn equals. Fn equals Fg cosine theta, because they have to be balanced. This is equal to ma in the x direction, but because Fg equals mg sine theta, as it is the case when gravity is the force that is causing the acceleration, these masses cancel, and you get that the acceleration equals g times a fraction, which is that fraction you would determine by using sine of the angle. For instance, if theta was 30 degrees, sine of 30 is a half, so the acceleration down the ramp would be half the free fall acceleration. The higher the angle, the larger the fraction will be, and so the higher the acceleration would be. But let's say the box was at rest. If the box is at rest, then you know that there can't be a net force, there can't be an acceleration, so fun must be equal to 0. Well, you're not going to get rid of Fgx entirely, so that's not the way to go. So to get rid of fun, you'll have to subtract from Fg a force, so that when you subtract those two, you get 0. So we can show that by taking an arrow the same length as this guy and pointing it the opposite way so that they balance, because the difference between them will result in no force left over. So again, what force provides that pushback? No other culprit but friction. So what is friction equal to? Friction is equal to mg sine theta, because they're balanced. Well, since we just talked about friction being equal to mu Fn, let's see what we get if we compare mu Fn to mg sine theta. So friction equals both mu Fn and mg sine theta. Maybe we can find some interesting relationship. Well, we said that Fn equals Fgy, which is Fg cosine theta, which is the same as mg cosine theta. So you plug that in here, and you also need your mu, and that equals mg sine theta. There's an m on either side, so the m's go away. And one interesting relationship is that mu has to be equal to, if we also see that there's actually a g on either side, so the g's go away. So I can divide both sides by cosine. I get sine over cosine, which equals tangent theta. And so you get this interesting little relationship here that the coefficient of friction should always equal the tangent of theta if you want the object that's sitting on that surface to remain at rest. So let's say in an example, you wanted to know whether an object was going to remain at rest on a surface, and you know what mu is, you can if you didn't know what the angle, if you knew what the angle was, you could plug the angle in and see if it equals mu. Now, if mu is greater, that's good news, because if mu is greater, then there's more friction available. So you have to at least top out whatever mu is. If your tangent of theta is less than mu, you're in good shape. Your object is going to stay there. So, but if I didn't know what the angle was, I could solve for the angle by taking the arctan or inverse tan of mu, and that would actually provide me with the angle that I would have to tilt my ramp at with this given mu value to make sure that the object, whatever it is, remains at rest. Remember, it's independent of the mass, so it doesn't matter what the object is. If I tilt the ramp, if I knew what the mu is, if I tilt the ramp at this angle, that object will not slide. Very interesting relationship there. Alright, this next point, number 5, is really important. I think it will help you to get many extra points earned here if you just pay attention to this little hint. It says, remember that there is no room for in between. So there are many questions that have choices which say, what will happen next? It'll be this, that, or it's going to be like this for a little bit of time, and then it'll do this, or first it'll do this and then do that. So Newton's laws are very cut and dry. If you've got balanced forces, you got constant velocity. If you got unbalanced forces, you've got constant acceleration. So objects can't just start to slow down after moving with constant velocity, unless all of a sudden you can say that the forces became unbalanced. If you know that for the entire duration of the motion, the forces remain balanced, then the object will always remain with constant velocity. The objects can't get tired moving, so they don't just run out of the ability to move. If there are no opposing forces, or the forces are balanced, then the objects will remain in motion. If an object has no forces, like in space, you throw a baseball, we can talk about it in the framework of energy as well. By throwing the baseball, you do work on the baseball, which increases the amount of kinetic energy that the baseball will have. The only thing that can change the amount of energy that the baseball has from there on out is work done from an outside force on the ball. So if you push the ball one way or the other, you will have effectively done work on it. So if I push the if I push the ball in the same direction as it was moving, I'd be doing positive work, and that adds kinetic energy to the ball. It will cause it to accelerate. If I have a force that's opposing the motion, then I'll be doing negative work, and that takes kinetic energy out of the ball and will slow the ball down. But if the ball remains in motion, unaffected by any force, the amount of kinetic energy that that ball will have will always remain the same. So if you draw pi to represent that ball, it'll be filled with EK, and no matter what time you look at it and where the ball is, if it's in deep space unaffected by any force, it can travel forever with the same amount of kinetic energy that it started with. It carries that energy with it. It does not need a force to keep it in motion. It doesn't need any extra energy to keep it in motion. It will continue in motion unaffected by being tired, by slowing down. There's no reason for it to slow down unless another force were to act on it. So it says beware of the choices which say it will move with constant speed for a bit, then slow down. Dynamics is pretty cut and dry. If there is a constant unbalanced force, the object will either constantly speed up, slow down, or change direction. If there are no forces or balanced forces, then the objects will maintain constant velocity, same speed in the same direction. That's it. All right, let's look at what we got next. All right, projectile motion. Like free fall, only gravity is acting on these objects. So we make the assumption that this is what being a projectile looks like via forces. We are ignoring the effects of any other forces except for gravity. The big one that we are ignoring, which sometimes misleads a lot of people, is air resistance. Air resistance is a very important force, oftentimes really hard to describe, because air resistance is determined by many different factors. So in more advanced studies, you would learn more about the effects of air resistance, but any real, if you really want to apply physics to the real world in terms of motion through the air, you're going to have to take air resistance into account. So that's a big part of any course in engineering or advanced physics studies. But we can create a simple model that's built from this fact that, or this premise, this assumption that Fg is the only force acting on our system. And that leads immediately to those two conclusions in number one, that in the x direction, because there are no forces, that any velocity given to the object forward or backward horizontally, that object will maintain that motion throughout. So if you throw a ball horizontally, it will not slow down horizontally. It will not speed up horizontally. It will maintain the same horizontal speed that you gave it. If you throw the ball at an angle, then you give the ball both a horizontal and a vertical speed at the same time. So you say, why just throw it upward or throw it sideways separately? Like, let me throw the ball forward, let me throw the ball up. You can combine the motions and throw it at an angle, and that effectively means that you're throwing both over and up at the same time. If this is your V initial, that's your hypotenuse of your triangle. If this is the angle that you know, this is the adjacent side, so this is VO cosine theta, and that's going to be our Vx. This is the opposite side, so for V initial y, that's VO times the sine of theta. So the quantity Vx remains constant throughout. So because we have constant velocity, delta x equals Vx times t, which equals VO cosine theta times t. In the y direction, we've got gravity to worry about. And gravity is accelerating everything negatively at minus 10 meters per second squared. So this arrow over time will get smaller until it reaches the top, at which point this arrow no longer exists. But what still remains, though, is this arrow. So when it's at the very top of its path, these two arrows are equal. This arrow is the only thing that remains. So the actual speed, I can like overlap this with a black arrow just to sort of illustrate that now this black arrow is now sitting on top of what was already the constant Vx component. So whatever V 0 cosine theta was, that's actually what the velocity is at the top. But on its way back down, gravity now can take hold of this object and give it speed back down. From an energy standpoint, we talk about gravitational potential energy, the fact that you're working against gravity. As you work against gravity, gravity stores, robs you of your kinetic energy, your motion energy, and stores it as gravitational potential. Now, gravity can only do negative work on the part of the motion that is upward. Right? So the object travels a distance that's pretty, some substantial distance, some arc length, but gravity, the work that gravity does is only dependent on the vertical distance. So that's why if we wanted to find EG, you'd be using MGH. So this is H. So that's not the distance that this ball would have traveled, but the gravitational potential energy is only equal to MGH. But at the top of its path, this projectile has both kinetic and gravitational potential. So you can calculate, if you knew what the max height was, you could calculate MGH, and it's an interesting problem here, because you could say that the kinetic energy that the object had before was all kinetic when it was launched, and at the top, because it still has velocity forward, that means that there's some EG and some EK. This EK is 1/2 mv squared, but particularly whatever v naught is, so that's where you would actually use this value. This is going to be 1/2 mvx squared. It's whatever, the speed up here is actually whatever Vx is. So if you knew what that angle was, you could actually figure out Vx and plug that in here and find what the kinetic energy would have to be. If you subtract that kinetic energy from this kinetic energy, you have what's left over, and that's MGH. You could actually use that to solve for H. So I don't believe that we actually did an example like that in class, but you could certainly use that, and it would actually, by writing those formulas out, you'd get the same exact equations that you would use. You would have used the time independent equation to figure out the max height in a situation like this, because you know what v initial is, you know what acceleration is, and you know that v final y is 0. So you can actually figure out the height using the time independent equation, v squared equals v0 squared plus 2a delta y, and that could help you to find delta y, which is the same thing here as h. So again, it depends on what you're comfortable with. If we read through some of these pointers here, the time an object spends in the air on Earth depends on height and does not depend on mass. All right, this is for horizontal launches, meaning that just like the Hot Wheels car, it leaves with this v initial only equal to Vx. So that means Voy equals 0. Then the amount of time that it spends in the air just depends on this height, because delta y equals 1/2 at squared plus voy t, but voy is 0. And so solve this for t, bring the 2 over, divide by a, square root, and so you can see that the time depends on the height. If I were to double the height, I would be in the air for a factor of root 2 longer, because by putting an extra 2 in here, that would come from doubling delta y. It would be related to this time if I had multiplied both sides by a factor of root 2. All right, another thing I could say is that if we were to quadruple the height, you'd put an extra 4 inside here, because before delta y would be 4 times the height, but the 4 can get square rooted to 2, and so you find out that if you were to quadruple the height, then it would spend 4 times as much time in the air. But you could have a big object, a small object, one large object, one small object. If they are fired with the same velocity, they will both travel the same distance in the same amount of time. Okay, because now the delta x, where it lands on the floor, is just equal to Vx times t. So if they're the same height, they have the same time spent in the air. If they're fired forward with the same speed, then they're going to hit the ground in the same spot at the same time. If you change the heights of these two guys, that changes the time that they spend in the air. If you put something higher up, this guy is going to spend, even if you gave him the same speed, that guy would spend more time in the air because delta y is bigger, so t would be bigger. But it is spending more time in the air means that it's able to go farther. If you give this object a larger speed, then it is going to, even though it spends the same amount of time in the air as this other guy that's moving slower, they'll hit the ground at the same time, but this one will go farther. So potentially you could allow for these two guys to hit at the same mark, but there's no way they would hit the ground at the same time. This one going faster will hit the ground first, not because it's moving faster, but because it's launched lower than this guy. All right, so this one will hit this. You can arrange to fire this object at a speed great enough so that it hits this target in the time that it has the fall. And at the same time, you could arrange so that this object that's at a higher height spends more time in the air at a slower speed, and given that it spends this extra time in the air, it will hit the same spot. So that's important to realize. Now, if you wanted to know the speed of the object at any point, the speed of these horizontally moving objects at the beginning is Vx. At any other point in time, it's a combination of Vx and Vy. Vx is whatever it was at the very beginning. Vy has been increasing since the time it started falling. To find the speed, you find the resultant. I'll put absolute value bars over those, and so the actual speed is then the square root of Vx squared plus Vy squared. Vx is the same number that you have at the beginning. Vy, one way, the easiest way that you could do that, depends on the information you're given. The easiest way would be if I told you that we're accelerating at -10 for a certain period of time. So you want to know how fast, after the object's been launched, how fast is it moving after 2 seconds. It has a Vx of 10 meters per second, and now after 2 seconds, Vy is -20 meters per second. So you have this Vx is 10, Vy is 20 meters per second. So you do 10 squared plus 20 squared, square rooted. Just for the sake of practice, let me do that for you real quick. 10 squared plus 20 squared, square rooted, is 22.4. So the object has sped up as we expected to, because it was it's falling, but the number might not be easily predictable if we didn't do it in this way. We were able to say that the Vx, which was 10 meters per second, is how fast it was initially moving forward. And now vertically, as it maintains that Vx, which is the same, it also has now gained 20 meters per second of speed downward. And so if we combined Vx and Vy using Pythagorean theorem, then you get 22.4, and that's going to be related to the actual speed that you would see on a speedometer that the object was carrying it with it through the air. Now, if you don't have the time, then you must have the change in the height, and you'd use the time independent equation. So the time independent equation is Vy squared equals Voy squared plus 2a delta y. So you can figure out Vy if you knew, in this case this would be 0. If you knew what delta y was, how far down it dropped, then you could figure out what Vy is that way. So it fell 10 meters. So if it fell 10 meters, delta y would be negative 10. And so you would do 2 times negative 10 meters per second squared times negative 10 meters. The negatives cancel, and so you get 200, and then you would do Vy is so Vy squared equals 200. Take the square root of both sides, and you got your Vy. You use Pythag, you can figure out the speed. Okay. All right. 3 says looking at a rescue plane, be able to trace the path taken by a package dropped from a plane from the ground perspective. You guys had a problem where you did this before. The plane is moving this way, and at this moment drops a package. So it maintains a Vx that is constant, the plane. So that is also going to be the same velocity that the package will have when it's dropped from the plane. And so, like any projectile, it's going to follow a curve. But at any point in time, the plane is always going to be over top of the package, as long as the plane maintains the same speed. So from the point of view of the people inside the plane, when they let go of the package beneath them, the floor opens up and they just drop the package. They keep looking at the package, and we are still in this framework where there's no air resistance. The package to them will appear to fall straight down and hit the ground. Whereas from the perspective from here, looking at it from the ground, you see the plane traveling forward, and you watch the package falling in 2 dimensions, forward and downward. So it's a combination of those 2 motions. If the plane were to speed up, then it would appear to the people on the plane that the package was being left behind. If there was air resistance, the package's forward motion would be affected. The air resistance would act against the forward motion of the package that it started with and slow it down forward. So if you maintain constant velocity from your point of view, the package will look like it will slow down and leave you behind. It looks like it'll you race ahead, and the package looks like it's being left behind. But in fact, it doesn't go backwards. To the point of view of somebody outside, even if there is air resistance, the package is let out of the plane and still travels forward a little bit before dropping straight down. That is with air resistance. I'm going to erase that now because I don't want that to affect your thinking. But assume no air resistance unless you're told to think about it. Alright, a rock is thrown horizontally off of a cliff, 45-meter cliff with an initial velocity of 15 meters per second. How far does the rock travel horizontally before striking the water? Okay, remember with projectile motion, you've got an XY table to worry about. And so we have delta x, Vx, t, delta y, Voy, V final y, a, t. The times in the air are equal. For horizontal launch, this is 0. This is always -10 if it's on the Earth. For situations where well, I'll start with this case where you know that the initial velocity is 15 meters per second. Because that's in the forward direction, that's completely Vx. If it was at an angle, you'd have to do trig first before finding out what Vx is, and then if it was at an angle, Voy would not be 0. The height is 45 meters. So it drops 45 meters, so you put minus there for drop. And so it would be minus 45 meters. So you want to find out how far. So that's this. So you have one equation that gets you delta x, and that's Vx times t. You have Vx, you need to find the time. So we had already looked at an equation for time, which says take the square root of 2 delta y over a. So I can do this all in one step. And you can check the math if you want to. I'm going to do it on my calculator also. So I'm going to do 15 times the square root of 2 times 45 divided by 10. The negatives cancel, which is good because you can't have a negative inside the square root. And you end up getting 45 meters. So just coincidentally, it makes it just as far forward as it does down in this situation. To try to use the horizontal distance to find the height, you'd just be sort of switching things around. If you knew what the horizontal distance was, you would use delta x and Vx to find t, and then use t to find delta y. So you could unexpand this back to delta y equals 1/2 at squared. And so you can find delta y if you knew what the time was and the fact that acceleration is -10. Alright, vectors. Oh, let me address part B first. If you have a second rock that's dropped the same instant that the first rock was thrown, as long as it is horizontally launched, then their y motions are identical. Their horizontal motions are different because the rock that's being dropped has no horizontal motion. The rock that is being thrown horizontally has horizontal motion. So the horizontally thrown rock from part A will have covered this 45-meter distance, whereas the rock that's being dropped in part B falls straight downward and covers no delta x. But they fall at the same rate, so they hit the ground at the same time. We were talking about how some other fast-moving projectile, like a bullet that's fired straight forward, ignoring air resistance, would hit the ground at the same time as a bullet that is dropped from the same height. The bullet would have traveled much farther because of its fast forward motion, but it will have spent the same amount of time in the air as a bullet that you just drop. Vectors have magnitude and direction. Scalars only have magnitude. So scalars are described just purely using numbers. Vectors can be described with arrows whose length represents the amount of the quantity that you're talking about. Whereas with a scalar, you just write down a number instead of a length. And the arrow also represents which way it's pointing would be the direction of interest. So types of vectors would be force, acceleration, velocity, displacement, your position relative to an origin. That should be the important ones. The scalar quantities that we've seen this year: time does not depend on direction, mass, energy, work. These are all values. Now these values can be negative in some cases, like work can be negative, just like temperature can be negative, right? But sometimes certain scalars are set on scales that have minimum of 0. So lengths can't be negative, because to have no length is as little as you can have of something. Time doesn't necessarily is not necessarily negative, although it could make sense in certain cases, because negative just could mean in the past. If you have the motion of the planets, for instance, they're going around the sun, you could plug into an equation that describes the circular motion of the planets, and you can plug in a negative time, and with that you could work backwards and figure out where the planet was months ago, instead of asking where the planet will be months from now. So that sometimes can be used as a negative value, but typically we use positive numbers for time, positive numbers for mass, positive numbers for length and distance, right? Anytime there's usually a negative, a lot of times that has to do with some direction that we've defined. So, all right, let's look next. So, an object is thrown. Now we have a situation where we're throwing at an angle. And so we've done components like this already. Vx, that you're told that the initial velocity is 15 meters per second and the angle is 20 degrees. Vx is VO cosine theta. VOy is VO sine theta. Alright. So make sure your calculator is set on degrees. If I do 15 times cosine of 20, I get 14.1. I'm just going to write 14 meters per second. And if I do 15 sine of 20, I'm going to get 5.1 meters per second. So this object is going to move forward at a speed of 14 meters per second to the right. So if you wanted to keep under this object, you'd run at 14 meters per second. Now, the fact that its speed upward is only 5.1, we know that gravity decelerates objects that are moving up at a rate of 10 meters per second per second. So it's not even going to take a second for gravity to slow this object's upward motion. right? It only has 5.1 meters per second of speed upward, and in 1 second gravity can decelerate you 10 meters per second in that 1 second. So it's going to take less than a second for the object to slow down and get to its maximum height, and then it'll take the same amount of time to come back down. If you want to find the max height occurs, it's the value of delta y when Vy is 0. So this is Voy is 5.1. The acceleration is -10. Vy is 0. You can pick the equation that doesn't have t in it to find out delta y. So I'm going to just do that in my calculator, and I'll put the answer, and you check to see if you can get the same answer that I do. So the max height should be about 1.3 meters. So I did that without knowing the time that it spends in the air. Now the max range, that depends on where it lands. The easiest case is if the object lands at the same height that it started from, because then delta y is equal to 0, because there's no change in height from the start of the motion to the end of the motion. And remember that delta x equals vxt. So vx is 14 meters per second. So you do have to know how much time it spends moving 14 meters per second forward. So you could now use y information to find the time by saying that this is v initial y, the acceleration is -10, and delta y is 0. So you could use the equation that doesn't have v final in it and solve for time. That's one option. The other option is saying that Voy, when it reaches this point, well, Vy, V final y, is actually going to be equal to -5.1 meters per second. It will be the same speed that it had going up. It'll now have coming back down, if it gets to the same position. If we were concerned about how fast it was going here, Vy will be less than -5.1. It could be -4, -3, something like that. If it lands after, then it would have a value that's greater than that, so -6, -7. Now that Vy is not the speed, remember? So if you want to find how fast it's actually going, you have to recombine Vy and Vx to find the resultant. So, but you do know what Vy is, so you could actually use the equation that doesn't have t in it again. Or sorry, you're looking for time. So you want to use the equation that doesn't make use of the knowledge here that we know, that delta y equal to 0. So it depends on what equation you like to use. I don't know. It's the preference that you might have. Because there's many different ways, depending on the information that you're given, to approach a problem. So you just have to show that you can do it one of those ways. So the speed just before it hits the ground should be identical. It should be 15 meters per second, because the fact that this is negative here implies that it's coming back down. But when I use Pythag to combine this 5.1 back with the 14, the negative 5.1 gets squared, and so it becomes positive, and so you don't have to worry about the fact that it's negative coming back down. The speed is one of those scalar quantities that isn't negative. You don't have any negative numbers on your speedometer. So it should have the same speed right before it hits the ground as it did when it was thrown up into the air. The speed at the max height is equal to 14 meters per second. That's because at max height it only has x velocity. So its velocity at the top is, it started out moving at 15 meters per second, and in the time that it spends in the air slows down very little. It only slows down to 14 meters per second and then speeds back up. Okay? Alright. So now the next piece here is relative motion. So the problems that we worked on were like the boat crossing problems, and that has a similar idea like projectile motion, that you can take what looks like one two-dimensional motion and break it up into two one-dimensional motions. So, and that is because of the forces that are involved and so on. But if we know that there's constant velocity any which way we're talking about, then we can use the constant velocity formula. So take the case where this is the bank of a river, and you have a boat that is going to travel straight to the right, but there is a current that is straight down the river. Then the boat's forward motion and the stream's down current motion will combine to give the boat, with respect to the shore, a motion that is faster and off course. So the captain is looking this way. He's looking, he thinks that he's going to go straight forward. He's facing the boat straight forward. And yet, by the time he gets to the other shore, he will reach this X location. Maybe intentional, maybe not intentional, but that's what's going to happen. If there was no current, then this wouldn't be here, and so you would just have this black arrow moving the boat straight forward. So we have the two equations for this, that we'll call this delta x, and we'll call this delta y. The current is Vy. The speed of the boat with respect to the captain on the boat with respect to the water is Vx. So the two equations, constant velocity, so it's Vx, delta x equals Vxt, delta y equals Vyt. If I know the width of the river and I know how fast it's going, I know how much time it's going to take me to cross. If I know how much time it takes me to cross and I know the current, I can figure out what the distance downstream I'm going to drift. So at the same time, if I drop a little buoy from the ship, the buoy is caught in the same current the boat is caught in. We will drift downstream at the same rate, but the boat will have crossed the stream and the buoy would only have drifted downstream. That's sort of the same idea behind the object that's fired horizontally, launched horizontally, and the object that's dropped. It's the same basic idea because they share a certain similar motion. In the case of the projectiles, they share the same y motion because they're both being accelerated by gravity. Here we have no acceleration, but they do still share the constant velocity that is caused by the stream current. So they're both being pulled downstream, and at the same time the boat is also moving across the stream, so that adds to the motion that the boat has, but they still have similar motions downstream. All right. Next up on the list is uniform circular motion and gravitation. So for UCM, that is constant motion around a perfect circle. So because it's a perfect circle and you're moving with the same speed, you are changing your direction at a constant rate. If you're changing your direction at a constant rate, you're also changing your velocity, despite the fact you might be keeping your speed the same. Velocity is speed and direction. So if either one of those is changing, you're accelerating. So you might be maintaining the same speed, but you are accelerating in a circle due to the fact that your direction is changing. And by moving at constant speed around a perfect circle, not an ellipse or any other drawn circle, it's got to be a perfect circle that could be defined by a radius, which is the measurement from the center to the perimeter, and that length is the same all the way around the circle, all the way around 360 degrees. So a couple things to point out here. So if this is a top-down view of circular motion, remember velocity is always tangential. Acceleration is always centripetal. Velocity and acceleration are always perpendicular. Force and acceleration are always parallel, or always in the same direction, in this case both centripetal. You have a centripetal force and a centripetal acceleration. So therefore the centripetal force and the velocity have to also be perpendicular. So the equations here we've used, I've showcased before when we were talking about forces. Fc equals MAC, that's F1 equals ma, or m times v squared over r. That the centripetal force is how much force you need to be going around, for a mass to be going around a circle of radius r at a speed v. Right? Then you have to decide what forces are there that could provide that centripetal force. Keep in mind, just remember I make that comment in part C of number 1. It's towards the center. If you see in a picture a vector that is pointing inside into the circle but not towards the center, that is not centripetal motion. That's not specifically uniform circular motion. So if the acceleration is not pointing towards the center, what that actually implies is the fact that the tangential speed is changing. So if there was an acceleration off at an angle, then the length of these red arrows would not remain the same. The length of the red arrows, if I had a vector that was pointing in this direction for acceleration, that would mean that in the next instant, when I draw this red arrow, the red arrow would actually be longer. It's still going around in a circle, but the speed is changing. So that makes it a little bit more complicated to study. You don't have to know how to do that for the final. So make sure you keep your accelerations pointing inward. I've talked about the hills and valleys and it's just similar to a Ferris wheel, and also similar to a roller coaster, in particular with the going upside down. We talked about that as well. The planets, this could be the Earth going around the Sun. This red dot could be the Earth, and the Sun could be in the center. And so if we assume that the Earth is going around in a circle, which actually goes against Kepler's first law, but it's an assumption we can make, just like we assume that there's no air resistance acting on our projectiles. We can get pretty decent numbers applying circular motion, pure uniform circular motion to the planets. You can get at least some decent idea of what's going on. There are satellites, though, that are placed into circular orbits, and so the circular motion equations are all we need to talk about the orbits of many different satellites. I do give you a problem in number 6. Let's take a look at that and what it's asking for. It says find the coefficient of friction needed to keep a car from sliding while moving around a 40-meter curve at a speed of 10 meters per second. So the car is going around this turn. Here's a top-down view of the car. So the velocity of the car can be described as tangential to the circle. The acceleration is in towards the center, and FC is also towards the center. So you need a force that will help the car stay in this turn. Well, where does the car want to go? If there were no forces present, the car would want to drift off in the direction that it's moving right now. So the car wants to travel this way. That would be the path that the car wants to follow. But it's not. It travels around the circle, and that's because there is a force pulling it inward, where you have the car trying to go out of the circle against the motion that the car wants to undergo. So you have a force that's going to be acting against the inertia of the car. Well, force that along the surface that acts against the motion, that sounds like friction. So we have a situation here that we say that Fc is equal to friction. That's what's keeping the car from slipping and moving out of the circle. Well, since Fc equals mv squared over r, and the frictional force equals mu Fn, we can work out what mu is. But we can boil this down a little bit further. You don't see it because this is up and down, but pointing up would be the normal force, pointing down would be gravity. And so those two forces along the surface would be vertically would have to be balanced. So Fn equals Fg. But Fg equals mg. So you have a mass on one side and you have a mass on the other. So that means the masses cancel. And like many problems that we've done, it looks like it doesn't matter what the mass of the object is, at least when you're talking about the quantities that are left over here. So in particular, we're looking for mu. So to solve for mu now, I'm just going to divide both sides by g, and you get this expression. So what does mu have to be? Now all I have to do is just plug this into my calculator. The speed v, I told you, was 10, so 10 squared divided by, and I'm going to make sure to put this guy in parentheses here when I'm typing it into the calculator. That's 10 times 40. So you have 10 squared is 100 divided by 400, so that's a fourth. So mu in this case equals 0.25. So that is, you need at least 0.25 mu equal to 0.25 in order to maintain this motion. If mu's larger, great, because then you can go faster. Going faster requires more mu. You can also go around a tighter circle. If r is smaller, that requires more mu. If mu is bigger, it works out fine. Because this is particularly, if we think back to our recent discussion of types of friction, this type of friction would actually be static friction. Okay. The last section on this page is then gravitation. First question, how does the force of gravity between two masses relate to the distance between them? How does the force relate to their masses? Force of gravity is directly proportional to mass. The more mass you have, the more gravity, the more the force of gravity attracts. It's related to the product of the two masses that are in the system. So you can't have gravity with one object. The Earth doesn't have gravity without another object that it's pulling on. So I have an M1 and I have an M2. They're separated by some distance d. They pull on each other. For every action there's an equal and opposite reaction. These two forces are equal in strength and opposite in direction. So the force of gravity is proportional to the product of the two masses. So if I double this one, the force of gravity doubles. If I triple just this one, the force of gravity triples. If I triple this one and I double this one, the force of gravity is now 6 times as strong. Okay? How it relates to distance is via the inverse square law. 1 over the distance squared. So if this distance doubles, the force of gravity, first of all, because it's inverse, drops. So the further apart they go, the weaker the force gets. But you have to square the difference in the distance. So the fact that we double the distance, you do double squared. So that's 4. And it's been cut by 1/4 of what it was. So it's now 1/4 the force that it used to be. So if there was a 40 Newton force of gravity between these two objects, but you double the distance between them, that force of gravity is now 10 Newtons, because you did 40 divided by 4, or 40 times 1/4, and you get that the force is now weaker by a factor of 1/4. So if same thing with gravity on the Earth, because Earth is just in this case one of the two masses that we're talking about here. So here's the radius of the Earth. So we define FG for us a distance of RE away from the center. If I were to stand on a ladder that is pointing away from the Earth, and this is also equal to the radius of the Earth, that means I've doubled the radius. This is now twice the radius of the Earth. So what happens to my weight? So here my weight was Fg. All right. So let's say that my weight was 160 newtons. How much do I weigh on top of this ladder? Well, I'm now further from the center of the Earth, so the force of gravity is less. So I will be lighter. I will actually be lighter. It's not like the the moving around a hill or on an elevator, I am actually as heavy as I feel. In this case, lighter than what I was. So standing on a scale, the scale would read a value that would be less than my weight here on the surface of the Earth. So I climb the ladder to the top, which is a huge distance of one whole Earth radius above the surface. That's equivalent to about 4,000 miles. So that's no joke. It's a very large distance, much more distant than many satellites that we have up in space. For instance, the space station is only 250 miles above our head. So I'm talking about 4,000 miles above our head. What would our weight be at that distance away from the Earth? Well, because you don't even need to know all the factors that go into this, all you need to know is that the only thing that changed, your mass and the mass of the Earth have not changed. So you don't have to know what the mass of the Earth is. You don't have to know what your mass was, even though you could easily tell that your mass is 16 kilograms, because you just divide by 10. So Fg is proportional to 1 over the distance squared. The masses do not change, so they're constant. So the only thing that we're trying to relate here is how gravity changed depending on the change in the distance. So I double the distance, so this d gets doubled, but think of the d getting also squared, so you have to square the 2 that now comes with the distance, so twice the distance. So you have to square the 2, so you get a factor of 4 out here on the bottom. So this is a factor of 1/4 that you get out here. So that 2 goes away now. So you have to multiply both sides by a factor of 1/4 to balance the relationship out. So just like we explained before, the force of gravity is at double the distance away is now 1/4 of what it was. So 160 divided by 4 is 40. So this person actually weighs 40 newtons at the top of that ladder. Right? That's how that works. So as anything moves away from the planet, whether it's a spaceship or just climbing a ladder, the force of gravity gets weaker as it inversely squared to the distance. You can calculate, if you want to actually calculate values of forces, then you need a full out equation, and that is Fg equals m1 times m2 divided by the distance between them squared, but then also multiplied, because this would have been a proportionality statement, so you need a constant of proportionality to relate these two terms, to actually set them equal. And so that constant of proportionality is what we call the gravitational constant, or Newton's constant, and that's 6.67 times 10 to the minus 11, and a bunch of units that just help to cancel things out and keep our units right. But it's a small number, so that means in order to get any real significant forces to work with, you're going to have to need large masses. So I will let you guys do number 3, but you know the 2 electrons have these masses, so you would plug them in once for M1 and another time for M2, which is the same value, and then this is the distance between the 2 electrons, which is, you plug that in here and square it, and you will be surprised how small that is. So at the quantum world, when you're talking about particles, gravity is not a force that easily fits in that realm, because you have other nuclear forces and electromagnetism that are really strong compared to gravity. And that's really been the huge debate today in modern physics, is to try to figure out where does gravity fit um, in the more comprehensive theories that govern the world of atoms, because everything is made of atoms. So the theory of the atom should hold for all objects, but it doesn't seem like gravity fits in too well at that scale. How do we figure out the mass of the Earth? Well, the mass of the Earth could be determined, like we did in class before, based on the fact that these two masses could represent, one could represent the Earth, and the other can represent you. Right? So this is your weight, which, if I erase this, your weight is equal to your mass times little g. But I have your mass on both sides. So now I know that little g is 10 newtons per kilogram. I know big G is 6.67 times 10 to the minus 11. And the distance between you and the Earth is the radius of the Earth. So the radius of the Earth is 6.4 times 10 to the 6 meters. 6,400,000 meters, or 6,400 kilometers. And you can solve this for the mass of the Earth, and you would find that the mass of the Earth is about 6 times 10 to the 24 kilograms. So that's how we know the mass of the Earth. If you want to work out the weight, your weight on another planet, you need to know what little g is on that planet. So if you got big G, you'd also need, instead of the mass of the Earth and the radius of the Earth, the mass of that planet and the radius of that planet. Once you know little g, that's the acceleration. That's if you take an object and you drop it, that would be the free fall acceleration. But Fg equals mg. So then all I would need to know is whatever your mass is, which is in kilograms, not in newtons. So if you know your mass, you know your weight on the Earth, you have to find what your mass is in kilograms, and then take your mass that's in kilograms and multiply it by the g that you found of your new planet. Now the other thing that I didn't put on the review that we've talked about in this unit for gravitation is Kepler's third law. And that comes from the fact that for a planet going around the Sun, the centripetal force is equal to the gravitational force. So mv squared over r equals g mass of the Sun times the mass of the planet divided by the distance squared. We lose an r. I should have erased this instead. You lose the little m, and so you get that the speed squared equals gm over r. There were questions on your UCM tests which this expression would have helped you guys think through when you're talking about satellites in circular orbits around the Earth, or if you were talking about the planet's motions around the Earth. But if the mass of the Sun were to suddenly increase, then in order to maintain the same radius, then you'd have to have a larger speed. Why? Because if the Sun were to suddenly have gotten bigger, it's pulling you faster, it's pulling you harder, so it's trying to whip you around faster. So you'd get pull in and you wouldn't be able to stay in your full circle. So in order to stay in the circle, you're going to have to try to escape it by going a little faster. And by going faster, you'll be able to stay in the circular motion that you want to. If the distance gets bigger, then the speed can be lower. And that's because the force weakens with distance. So if you go farther out from the sun, then it's not pulling you as hard, and so you don't have to whip around the sun as fast to keep from falling into the sun. Remember, all objects that are in orbit are freely falling towards the sun. All right, but they're moving so fast tangentially that they end up falling around the sun instead of falling into it. But if the planets were to ever slow down for any reason, they would immediately start to move inward towards the inner part of the solar system, towards the sun. Now, if we want to relate time, since v equals 2 pi r over t, big T is the period, so that's how much time it takes for a revolution. So if it takes you 1 second to revolve around the circle once, then big T is 1 second. But this is, because this is constant velocity, this is really just distance over time, right? So that's where that comes from. This is the full circumference, distance around the circle. This is the full time that it takes to go around the circle once. So I want to relate to v squared. So v squared equals everything in here squared. So 2 squared is 4. You have pi squared, r squared, t squared. So I get 4 pi squared r squared over t squared equals g m over r. If I rearrange this a little bit, I bring big t squared upstairs. I multiply both sides by r, and I get an r cubed. And then I have a bunch of constants in here. So what I'm left with is 4 pi squared upstairs, and then g times the mass of the sun downstairs. So if you knew what the mass of the sun was, you could figure out this constant. Multiply this constant by the distance that you are from the sun cubed, and that equals the time that it takes you to go around the sun squared. That's called Kepler's third law, using Newton's law of gravity, though. So these are in the standard units of meters and seconds. But we also talked about in class the fact that if you were to reduce the units here to be specific quantities, that we could simplify this equation down a little bit. I could set this whole thing equal to 1, given that I measure the time in years, and I measure the distance in what we call an astronomical unit, which is the distance from the Earth to the sun. So if you're told that the distance to a planet, like Pluto, for instance, is about 40 times the distance that we are from the sun, then you can plug in that 40, cube it, take the square root of that, and you can find how many years it takes to go around the sun. So you just have to be aware that you could use this simplified equation that doesn't incorporate all these crazy numbers, and get good answers as long as you use the right units. So just don't mix that up at all. Alright, last page. So what is considered work in the physics sense? That's whenever a force causes a change in motion. So forces can act on a system, but if they're not responsible for the motion that you're trying to observe or measure, then that force is not doing that work. So we define work as F delta X cosine theta. And I won't get too much into detail here. You can look at my video on the review for the last quiz that you guys took for more energy concepts, but we talked about how the force, if the force is like to the right and the motion is to the right, the angle is 0 degrees, and so you'd have cosine of 0 to be 1, and so you'd have the maximum amount of work that can be done because you'd be doing force times delta x. So if you're trying to find work, here's your force, here's your distance, here's your angle, plug it into the formula. If you want to find the work done by friction to slow down an object with a certain speed, all right, how do you figure that out? Well, the work done by friction, so an object that starts out with some speed, starts out with EK, that speed is then turned into EQ. EQ equals the work done by friction. But these two are equal. So if I find the kinetic energy, that equals the amount of EQ that is now in the surface. Friction has done the work to decrease the kinetic energy I have and increase the amount of internal energy that's in my system. And so we can find how much work is done by friction just by finding EQ, which is done by finding the kinetic energy. So if you just do EK equals 1/2 mv squared, 1/2 the mass. The mass is in kilograms, so don't add any extra zeros or anything like that to it. So you want to keep the mass in kilograms and then multiply it by 23 meters per second, the whole thing squared. You'll get your answer. And that you can, if you want the energy, you can write it in terms of joules. And if you want the work that's being done by friction, then it is in Newton meters. So friction is doing negative work. So when this increases, that means the work I'm doing is negative. So you want to put, if you want to put that out front just to remember, you can. But just remember that friction is always doing negative work. So when you get an increase in EQ, that means you got a non-conservative force doing negative work. It's similar with the potential energies, except potential energy is usable because you're just storing it. But when gravity is doing negative work, you're increasing the amount of EG. When the spring force is doing negative work, you're increasing the amount of EEL, the elastic energy. So this is an example of the work energy theorem. The work that's being done by forces changes the energy in the system. How does the stopping distance relate to velocity? Well, if you know that EK equals 1/2 mv squared, this is where your velocity term comes from, and that equals the work that's being done by friction. The work done by a constant frictional force is FF times delta x. So the stopping distance is just whatever the kinetic energy is divided by the force of friction. So you'd have to know a little bit more about the friction in the surface to actually carry out a problem. In particular, you need to know mu. Find the gravitational potential energy of a 900 kilogram roller coaster at a height of 85 meters above the ground. To find that, the equation for EG is mgh. The mass is 900 kilograms. You have to plug that in for m. Plug in 10 for newtons per kilogram for little g, and then 85 meters for h. And then you'll have your gravitational potential energy in joules. If this is your roller coaster, the roller coaster always has its greatest amount of energy. You have like the typical rides where the some conveyor brings the car up to the first hill, and then it will likely rely on conservation of energy to move it around the rest of the track. But it's got the most energy that it'll have when it's at the very top of this first hill. It's all EG right now. As it goes down the hill, that EG is turning into EK. If it gets to the very bottom here, then all the EG is now EK. It'll go up, and so some of the, working against gravity, some of that EK becomes EG again. When it gets to the top of this hill, it doesn't come to a stop because there's still all this distance between its initial height and where it is now. So it's going over that hill with some speed. So engineers have to work that out, because remember, now you're going over this hill. That's like circular motion now, and so you need a centripetal force. So you have to make sure that you can go over this hill at the right speed, so that you're not, you don't want to build this too low or too high. Building it too high might, you definitely don't want to build it above this line, because then it won't make it. It'll start going back the other way. But putting it too low might make you go too fast over this, and so it might have more speed than the centripetal force that can be provided, and so you don't want to run the risk of having the roller coaster car go off the track. So if the roller coaster in number 6 is allowed to fall from rest from that position, what would the speed at ground level be if there was no friction acting? You would take EG, which is at the top, and set that equal to EK at the bottom. If you already calculated what EG is from that formula up there, then since EK equals 1/2 mv squared, you can just now solve for V. What would happen if the roller coaster in the previous problem did encounter friction? That is the case where you'd have EQ come into the situation. And if that's the case, if EQ comes into our system, then, for instance, if you're going over this hill without friction, there might be you might reach a certain speed. But with friction, the speed would certainly be less, because the whole time that you're going through this track, friction is taking away from the energy in the system. Okay. Explain the energy conversion that a skier undergoes as they start from rest at the top of a hill to the bottom of the hill. How about a pendulum? How about a mass launched upward from a spring? So these are all similar cases that we've dealt with before. Let me go to a bigger page here. So if you have a hill, you can determine, if you want to figure out how fast the box is going when it gets to the bottom of the hill, if the surface is frictionless and the initial velocity of the box is 0, that means that the initial energy is all EG. EG is measured not by how far it is this way, but by the height it is above some level that we set the potential equal to 0. So this is our height. So you take this mass, and EG equals mgh, and when it gets down to this level, it will have picked up a certain amount of speed, and all of this EG becomes EK. EK is 1/2 mv squared. So mgh equals 1/2 mv squared. The masses cancel. The speed squared has to equal 2gh or the square root of 2gh. We could have done the same thing using fun equals ma. How would we have done that? We could have, if we're assuming there's no friction and the forces are don't change, they might be unbalanced, but they're not changing. You can draw yourself a free body diagram. I'm going to skip that step, and you can realize that fun for this system is mg sine theta. Now you say, okay, you don't know what theta is. It's going to be that angle there, but you might not even know what it is. And that's okay. You don't need to know. Because ultimately, it doesn't depend on the angle. So we'll have to get rid of it somehow. Well, the acceleration is fun over m. So if I divide fun by m, you're just left with g sine theta. Well, now I know the acceleration. I know v initial is 0. And I'm looking for v final. I don't have time. What I would need, though, is if I don't have time, then I need a distance. But the distance that I would want would be the distance downhill. What I have, though, is h. I have the height. So it's the opposite side of this triangle. So sine of theta equals opposite over, I'll call this delta x, hypotenuse. So this is why we don't need the sine, because anywhere we see a sine of theta, we can actually replace it with h delta x, h over delta x. But let's first sort of figure out, we're going to use the equation that doesn't have t in it, so that's v squared equals v initial squared, which is 0, times 2a delta x. But a is g sine theta, but sine theta is h over delta x. So in for a, you got g sine theta, and then you have this delta x here. Well, look at that. So now you have this delta x canceling with that delta x, and you get v squared equals 2gh, or v equals the square root of 2gh. And that matches that description perfectly. So you could use energy, you could use fun equals ma and kinematics, and get the same result. The more experience you have with these topics, the more you find out that there are going to be certain circumstances where energy works better than kinematics, and sometimes kinematics might be easier than the energy. All right. Kinetic energy depends on speed and mass, 1/2 mv squared. Elastic potential energy, EEL, is 1/2 k delta x squared. K is called the spring constant. It has units of newtons per meter. Delta x is the amount of stretch measured from the equilibrium position. So if this is the normal length of a spring, then this is x equals 0. And I take that same spring and I stretch it to this new location. And this is delta x. All right? It's the amount of stretch. So you can store energy in the form of elastic potential by knowing what the spring constant is and knowing how much the spring has been stretched. Hooke's law comes from the fact that Hookean springs behave in the way that the force of the spring is proportional to the stretch. You get a straight line. So the strength of the force grows with the stretch. It's always opposite in the direction of the stretch, though. So if I pull to the right, the force is to the left. If I push to the left, the force is to the right. So that's why there might be a a negative sign that comes up when we write the formula down. But if you want to get the full equation, you need the slope. The slope is the spring constant. So that's how we find what the spring constant is we test the springs. We see how much force it takes to stretch them, and then you can determine by finding the slope what the spring constant would be, and that's how the manufacturers will describe how strong the spring is. So if the spring takes more force to pull, they would appear as having larger slopes on this graph. So the spring force is equal to the spring constant times K, and if you're concerned with the direction, then you could put a negative out front of there. It's always against the direction of the stretch or compression. The area under this graph is the work that's done by you or by the spring in stretching it to whatever this length is, but it's also the amount of energy that's being stored as EEL. You can find that by using the area. Okay. The last topic on here deals with our past labs. Alright, so let's take a look at that real quick. So here are a list of all the different labs that we've done throughout the year. The buggy lab, that's where we looked at constant velocity. We showed that when we graph position over time, we would get a straight line where the slope is the velocity. This is an example of a proportional relationship. X is proportional to t, and when position is proportional to time, when you cover equal distance in equal amount of time, that means that you're moving with constant velocity. And so our change in our position equals the velocity times the change in our time. The crash lab, we put two cars facing each other and predicted where they were going to crash by producing two different equations and finding where they intersect on the graph. The incline rail lab was our first look at acceleration. So in that lab, we had a car that we put on a track that goes down a ramp, and because it was accelerating due to the x component of gravity, it was accelerating at a constant rate. So when we graphed the x position over time, we found this parabola. So we suggested that x was proportional to t squared. So when x is proportional, when the position is proportional to the time squared, that implies a constant acceleration. And to straighten this graph, you need to square the times, and the slope equals half of your object's acceleration, which is the first place where we found that delta x equals 1/2 a times t squared. The free fall lab was where we found out that the free fall acceleration was 9.8. The statics lab was the stations that we had, where you had to go to the different stations and determine missing pieces, forces, masses. But statics means that all the forces were balanced, so you had to show that they were all balanced and work out whatever quantity was missing. The fun lab was the modified Atwood machine, which is the car on the table pulled by a string which was attached over a pulley, and there was some mass that was at the end of that string. The mass is being pulled by its own weight, by gravity, and we kept that the same. The tension is equal throughout, So the tension here cancels with the tension there. So the net force of the system, so we used the fun for the system was Fg of the hanging mass. But what we did was we varied the different masses that were on the car, and we graphed the resulting acceleration versus the mass. And what we found there was a hyperbola. So that suggested to us that the acceleration was inversely proportional to the mass. And to straighten that graph, you had to do 1 over the mass. And what we found the value of the slope to be was fun. And when we looked at the units, since acceleration has units of meters per second squared, and this has units of 1 over kilograms, when you do rise over run, you get meters per second squared over 1 over kg. To simplify that down, multiply the numerator by the reciprocal of the denominator. That cancels all this stuff out, and you get kg m over s squared. Well, that's one of these equals 1 Newton. That's how we define a Newton, as 1 kilogram meter per second squared. So the units for this slope is in fact units of newtons, and so that's how we were able to make sense of the fact that the slope actually did represent fun. And since that was our constant of proportionality, A equals fun times 1 over m, or just divided by m. And if we solve for fun, that's the first time we were introduced to fun equals ma. The projectile motion lab showed that with gravity being the only force acting on the object that we were throwing around in the gym, that we were maintaining constant velocity in the x direction and constant acceleration in the y direction. So we had collected data. So in the app that we used, it gave us the x coordinates and the y coordinates, and it plotted them with respect to time. It showed that the x motion was constant, and that the y motion was not constant. It was accelerating, and this was able to tell us the Vx from the slope, and the equation for this curve gave us 1/2 of a, which was close to -5 because of the fact that it's half of -10, times t squared plus VOY times t. So we were able to use like a quad reg option on the calculator that provided us with even the this VOY term. And so we could even have looked at what the initial speed of the ball was by taking our Vx, squaring that, times VOY squared. So that's what we did for the projectile motion lab. The Hot Wheels lab, you predicted the crash site of a Hot Wheels car that was launched horizontally from the table. So you were trying to predict delta x. So delta x equals Vxt. So you needed to know the time spent in the air, which is equal to 2 delta y over a. So you needed to know the height, and a was -9.8. And I found the time in the air for you, so you'd also needed to know what the speed was leaving the table. The speed you found out by using the photogate sensors. The UCM lab was the stopper on the string, and the information that we graphed here was V with respect to R. So you had to keep in mind that we kept the force constant, so Fc was constant, so that means the acceleration was constant, because the mass of the stopper never changed. So we were looking how the speed was changing with different radii, given that the force and the acceleration were constant, and what we found was an overcurve. So that suggested to us that v squared was proportional to r, and based on the units, because this is in, if we try to straighten the graph, you want to square the v values. R would remain the same. This becomes a straight line. Meters squared per second squared over meters gets me meters per second squared. That's the same units as the acceleration. And so we were able to say that v squared equals ac times r. We had a way of confirming that, because if you knew what the force was the tension, but that was equal to the weight of the hanging washers. So we were able to find out what the force was, divide it by the mass of the stopper, and we were able to work out what the centripetal acceleration was. So, and compare it to our slope, and found that they were very similar. And the spring lab was something that we had done recently to show that the force of the spring versus the stretch were proportional, that the force of the spring grew the greater that we stretch the spring. Okay, so the exam goes over the span of 3 days. So you have plenty of things to look at, look back on, make sure you study, and good luck.